right now, thousands of invisible bullets from deep space are passing straight through your body. You cannot see them, you cannot feel them, but they are ripping through your DNA as we speak. They are called cosmic rays, and they have been attacking Earth every second for billions of years. In 1912, a physicist named Victor Hess risked his life to prove they existed. He flew a balloon. He carried radiation detectors up to 5,300 meters, higher than any mountain. Everyone expected radiation to decrease at higher altitudes. The results shocked the whole world. Radiation was 3 times stronger up there. It was not coming from Earth. It came from outer space. He even flew during a solar eclipse to prove it was not the sun. It came from beyond our galaxy. Hess won the Nobel Prize in 1936, but his discovery opened a mystery that lasted over a century. Where exactly are these particles coming from? What in the universe could produce such raw energy? To understand this, you need to know what cosmic rays actually do when they hit our atmosphere. A single proton traveling at nearly the speed of light smashes into an air molecule high above us. That collision creates a shower of millions of secondary particles that rain down toward the ground. Muons, neutrons, electrons, positrons, and gamma rays scatter in every direction like shrapnel. These particles hit satellites, corrupt their circuits, and have caused real spacecraft to fail. They reach the surface, too. They pass through buildings, through concrete, through you, right now. Airline pilots and flight crews receive more radiation from cosmic rays than nuclear plant workers. So scientists mapped how many cosmic rays arrive at each energy level. They plotted a spectrum graph. At low energies, billions arrive. At higher energies, fewer and fewer. The line drops steeply down. But at one specific point, the graph bends sharply. Scientists named this strange bend the knee. Beyond the knee, above 4 quadrillion electron volts, cosmic rays become incredibly rare to find. Less than 1 particle per square kilometer per century hits Earth at the very highest energy levels. Some scientists believed the knee marked a boundary, below it our galaxy, above it far beyond. But nobody could prove it. Nobody could trace where these particles were actually being launched. The problem is magnetic fields. They bend cosmic ray paths like a curved mirror bends your image. By the time a cosmic ray reaches Earth, its original direction has been scrambled beyond all hope. For over 100 years, scientists had no way to trace them. The mystery seemed completely stuck. Then, China built something extraordinary in the mountains of Sichuan province at 4,400 meters. The Large High-Altitude Air Shower Observatory, LHAASO, the largest cosmic ray detector ever built. It covers 1.36 square kilometers. That is the size of 190 football fields. Nearly 10,000 individual detectors spread across ancient glacial terrain on Hai-Z mountaintop. 3 types of detectors work together: electromagnetic sensors, muon detectors, and water tanks. The water tanks are massive, 78,000 square meters of purified water with light sensors. When a particle hits the water faster than light travels through it, it creates a blue flash of light. This is Cherenkov radiation, the same physics that makes nuclear reactor pools glow that eerie blue. 18 wide-field telescopes scan the sky above, watching for the faintest flashes in the atmosphere. Together, these systems can catch a cosmic ray shower and work backward to identify what caused it. With only half the observatory built, LHAASO made a discovery that stunned the astrophysics community. They detected gamma-ray photons with energies exceeding 1 quadrillion electron volts, 1 full peta-eV. Then they found one at 1.4 peta-eV, the single highest energy photon ever observed by humans. For perspective, that is 150 times more energy than the Large Hadron Collider makes. One single photon carrying the energy of a ping-pong ball falling off a table in one tiny particle. That amount of energy does not appear from nowhere. Something out there is creating these monsters. Scientists had theorized about such a source for decades. They gave it a name before finding it.
PeVatron, any cosmic object capable of accelerating particles to 1 peta-eV of energy. LHAASO proved PeVatrons are real, but proving they exist and actually finding them are very different. Here's where gamma rays helped. Unlike cosmic rays, gamma rays carry no electric charge at all. That means magnetic fields cannot bend them. Gamma rays travel in perfectly straight lines forever. So, LHAASO traced the gamma rays backward, like following bullet trajectories back to a hidden sniper. They mapped 12 distinct sources across the sky, 12 directions where peta-gamma rays came from. But there was a problem. A line of sight stretching into infinity does not tell you the distance. Except scientists knew one crucial fact: ultra-high-energy gamma rays cannot survive long journeys. Space is filled with ancient photons left over from the Big Bang, cold, low-energy background light. When a peta-gamma ray hits one of these background photons, both are destroyed. They simply vanish. This means peta-gamma rays cannot travel across galaxies. They would be absorbed long before arriving. So, if LHAASO detected them here on Earth, these 12 sources had to be within our own Milky Way. That one finding changed everything. The knee in the spectrum was not about extragalactic cosmic rays. The most powerful particle accelerators in the known universe were hiding right here in our galaxy. So, what objects could possibly produce these insane energies? Scientists had 3 main candidates. First, supernova remnants. When a massive star explodes, it drives material outward at extreme speed. Just ahead of this material, a shock wave forms, a wall of compressed gas, magnetic field, and heat. Particles bounce back and forth across this shock front, gaining energy with each crossing they make. This process is called diffusive shock acceleration. Scientists also call it the Fermi mechanism. But there's a catch. Supernova remnants can only do this during the first 100 years of their life. Every supernova remnant we know is much older than that, so how could they still produce PeVa particles? Some particles escape early and get trapped in nearby giant molecular clouds full of dense, cold gas. Inside those clouds, they collide with gas and produce gamma rays reaching 1 quadrillion electron volts. Second candidate, pulsars, rapidly spinning neutron stars with magnetic fields trillions of times Earth's. Their rotation generates powerful electric fields that rip electrons right off the stellar surface. These electrons form a wind of particles expanding outward at nearly the speed of light from the pulsar. When this wind slams into surrounding gas and dust, it creates a termination shock boundary layer. At that shock point, particles are accelerated to extreme energies, over 30% of candidates. Third candidate surprised everyone. The spectrum showed an unexplained bump hitting inside the knee. These particles did not match supernova remnants or pulsars. Something else entirely was making them. The answer turned out to be nature's ultimate particle accelerator. Black holes themselves were doing it. In 2009, 3 scientists proposed that particles colliding near a black hole's event horizon could work. If 2 particles collide right at the edge, they could theoretically reach near unlimited energy levels. Everyone dismissed it. Those particles would just fall into the black hole and be lost forever, right? Wrong. Newer models revealed that some fraction of those particles actually get ejected back outward. LHAASO found proof in the Cygnus region. An X-ray binary system called Sigmus X3 stood out clearly. It has a Wolf Rayet star feeding material to a black hole. Massive jets of plasma blast from its poles. Scientists noticed the gamma ray signal had a repeating pattern, every 4.8 hours exactly. That matched the orbital period of the black hole circling its companion star. The signature was proof. Cygnus X3 was producing gamma rays at 3.7 peta-eV, far beyond what a normal PeVatron makes. The protons creating those photons must carry at least 10 peta-eV. This was a super PeVatron in our galaxy. Since LHAASO's first catalog in 2023, the number of candidate PeVatrons has exploded to over 75. Our Milky Way was thought to be a quiet, peaceful galaxy. That assumption has now been completely shattered. We are surrounded by natural particle accelerators far more powerful than anything humans have ever built. The cosmic rays are still coming, every second, every day, passing through everything, including you. But for the first time in a century, we finally know where they come from, and that changes everything.
If this changed how you see the universe, like the video and subscribe for more cosmic mysteries.